So welcome to all in the third video lecture of subject digital signal processing. The topic is FIR filter design. So here in this particular video lecture we will see that how FIR filter can be designed. I am Dr. Amit Garg, Associate Professor in EC Department of AKGEC. So let us start with the design techniques for FIR filters. So if we will see that well-known methods of designing FIR filters are as follows. First one is Fourier series method, then window method, then frequency sampling method and optimum filter design method. So these are the methods that we generally use for the designing of FIR filters, because as per the curriculum AKTU, I am only considering this window method. So here we will see that how FIR filter is designing using window methods. Okay. So if we will see window techniques, so we will see before going through this window techniques, we should understand about the background of this. So if you will see the frequency response of a digital filter, it is periodic with period equal to the sampling frequency. Okay. So if we will see the desired frequency response of an FIR digital filter, it can be represented by the Fourier series. Like this is the desired frequency response and it will consist of terms hd to the power j omega equals to summation n equals to minus infinity to infinity hdn e to the power minus j omega n. It means the impulse response is lying between minus infinity to plus infinity, and if we want to calculate HDN from it, then we can calculate the HDN using this expression. Okay, because your spectrum hd to the power j omega is continuous, so we have to use integration sign and minus pi to pi, because it is continuous extending from minus infinity to infinity, but it is periodic also with period 2 pi. So that's why we have taken the limit minus pi to pi. You can also write it 0 to 2 pi. Okay, so this is how we can obtain the desired impulse response. Now, if we will see this Fourier series, the Fourier coefficient of this series HDN are identical to the impulse response of a digital filter. There are two difficulties with the implementation of equation 1 for the designing of a digital filter. So, if we will see this equation number 1, and we are seeing that here impulse response is taking the values from n equals to minus infinity to plus infinity. So, you can say impulse response are having values from minus infinity to plus infinity. But if we want to implement such a filter, then there are two difficulties which are arising basically for the implementation of it. What are two difficulties? First difficulty, if we will see, then impulse response is of infinite duration, and second one is impulse response is non-causal. So because impulse response is non-causal and also it is of infinite duration, because the impulse response is non-causal, so this type of filter is basically non-realizable filters. So we cannot design these filters using FIR techniques. So what we have to do, out of these two difficulties, if we will see, the actual difficulty is that it is of infinite duration. Because if it is of finite duration, then we can make it causal. Causality is not an issue if sequence is of finite duration, because if sequence is of finite duration, let us suppose from n equals to minus n to n, then we can make it causal easily by providing n amount of delay in it, so that impulse response will become causal. So here if you will see, the actual issue is that impulse response is of infinite duration, and causality is not an issue if impulse response is of finite duration, because if impulse response is of finite duration, then we can always make the impulse response causal by providing finite amount of delay. So this is written here. First, the impulse response is of infinite duration, and the second, the filter is non-causal and unrealizable. So even if I am not taking the second condition and impulse response is of infinite duration, so no finite amount of delay can make the impulse response realizable. Hence, the filter resulting from a Fourier series representation of h to the power j omega is an unrealizable IR filter. So the infinite duration impulse response can be converted to a finite duration impulse response by truncating the infinite series at n equals to plus minus n. So what we will do, because we have seen that HDN cannot be realizable because of infinite duration. So what we will do, we will take a window function. Let us say window function is a finite duration function Wn. So we are taking a finite duration function so that we can convert our infinite duration impulse response into finite duration impulse response. So let us suppose this is our infinite duration impulse response and this is the finite duration window function, and if we are multiplying it, let us suppose we are getting Hn. So this time the value of Hn will become finite duration, if this Wn will be of finite duration. Okay, so so this is the basically the main aim. Main aim is that we are having a finite duration impulse response, or if we are having a function which is extending from minus infinity to infinity and we want to make it causal. So for making it causal, we are multiplying it by a window function which is of finite duration. So if we are multiplying a infinite duration sequence with finite duration sequence, then we will get a finite duration impulse response. Okay, so that's why it is written over here, the infinite duration impulse response can be converted to a finite duration impulse response by truncating the infinite series at n equals to plus minus m. Okay, but if we will simply truncate, means how we can truncate? If we will simply multiply this, and the role of window function or the shape of window function is that it will be abruptly truncated. So if the truncation will be abrupt, then we are getting the undesirable oscillations in the passband and stopband of the digital filter, which is not desirable. So what we want? We want that in the process of making it finite, if we are multiplying by a window function Wn which is of finite duration, so that this window function should have shape, so that the truncation should be gradual, not abrupt. Because if abrupt truncation will be there, then we are having undesirable oscillations in the passband and stopband of the digital filter. So here comes the important concept of window shape. Like we are having various type of window shapes. Like if we are taking a rectangular window, I am just drawing the envelope here. Otherwise, if you will see a window function, rectangular window function, it is of like this, 0 to m minus 1. Or if we are taking symmetric, then it will become 0 to minus m minus 1 by 2 to m minus 1 by 2. If in either of the case we are having this, but when we are using this rectangular window function, then what happened? This truncation is abrupt truncation, and due to this abrupt truncation, what happened? We are having undesirable oscillations. Okay, so we can see this is due to the slow convergence of the Fourier series needed near the point of discontinuity. These undesirable oscillations can be reduced by using a set of time limited weighing functions, Wn referred to as window function, to modify the Fourier coefficient. So first window function that we will see is the rectangular window function, but in the case of rectangular window function, when we are using this type of rectangular window function for the truncation of this infinite duration impulse response, then when we will design the filter, then filter will having undesirable oscillations in the passband and stopband. So we have to choose window functions, although rectangular window is also window function, but actually we cannot say rectangular window function is an appropriate window function, because it does not having the desirable properties of the window function. Okay, so we can see this process here by this figure. So this is the HDN, or the desired impulse response. So you have seen that desired impulse response will consist of infinite number of terms. So this is extending from minus infinity to plus infinity. And we are taking a window function. Let us suppose our window function is like this. So you can see here, within minus n to n, only elements are there, other elements are 0. So this is a finite duration impulse response, and we are multiplying these two window functions in time domain. So we will get Hn. So you can see this time, wherever these values are occurring, we are only getting the output accordingly. Okay, so we will see, because this window function is varying from minus n to n, so we are having HDN values only between minus n to n. So we are having these values between minus n to n. So this is your finite duration impulse response, and this is your infinite duration impulse response, and this is your finite duration window function. Okay, so this is the process of obtaining Hn. Hn is obtaining by Hn equals to HDN multiply Wn. Okay. Now if you will see this in frequency domain, so we will see this is the desired frequency response in frequency domain. It is periodic with period minus pi to pi, but it is continuous within minus pi to pi. How we will obtain it? We will simply take the DTFT. If we will take the DTFT of HDN, we will get HD e to the power j omega. Okay. Now this is window function Wn. Corresponding to this window function, if we will take DTFT of this window function, we will get window function W to the power j omega. Okay, so we are having some sort of this type of function we are getting, again it is continuous. Okay, so we know the operation that is performing in time domain is basically the multiplication, so that we are getting the output. But in frequency domain, if you will see, multiplication in time domain corresponds to the convolution in frequency domain. So that's why h e to the power j omega that we are obtaining is basically how we are getting this h d e to the power j omega convolution w e to the power j omega. So we are having this type of response. Okay. Okay. So this is the time domain representation and this is the frequency domain representation. One important thing is there that impulse response here is of finite duration, but it is non-causal. It is non-causal. So we have already discussed that non-causal filters cannot be realized. So we have to make it realizable. So how can we make it realizable? If we will simply delay by n samples. If we will delay hn by n samples, so that this sample will occur over here. Okay. So we are having a new sequence, let us say gn, which is delayed, which is obtained by delaying hn by n units in time, so that this sample will start from here. Okay. So that's why you can see it, we can make it causal. So this is the causal one. So gn is the causal version of hn. hn is non-causal, but gn is the causal one. Okay. So desired frequency response h d power j omega and its Fourier coefficients are shown at the top of the figure. The finite duration weighing function w and its Fourier transform are shown in the second row. The Fourier transform, the weighing function consists of a main lobe which contains most of the energy of the window function and the side lobes which decay rapidly. So if we will see the this frequency response of the window function, that we can say this is the main lobe. This is the main lobe. And other are side lobes. These are side lobes. So basically what we want with our spectrum, what we want with our frequency response, or what type of frequency response should have a window function. So that frequency response should be like that all the energy should be concentrated over this main lobe only. So there should be no side lobes, or very less number of side lobes will be there, because side lobes are nothing but spectral leakage. Okay, so if you will talk about a ideal window function, that ideal window function should have like impulse sort of, means all the energy will be concentrated over a impulse and all other side lobes will not be there. But this is the ideal situation, and in the practical situation what we should what we require with the window function, that most of the energy should be concentrated over this lobe. So what happened when most of the energy is concentrated here, then this width of this main lobe should be as small as possible, so that its height will become higher. Okay. So this is the desirable property of the window function. The sequence hn equals to sdn w obtained to get an FIR approximation of s d power j omega. The sequence hn is exactly 0 outside the interval minus n to m. The sequence hn and its Fourier transform are shown in the third row. h to the power j omega is nothing but the circular convolution h to the power j omega and w to the power j omega. So this we have already seen. The realizable causal sequence Gn, which is obtained by shifting Hn, is shown in the last row, and this can be used as the desired filter impulse response. Okay. Now we will see that how this window function effect. So a major effect of windowing is that the discontinuities in h to the power j omega are converted into transition bands between values of on either side of discontinuity. The width of these transitions band depend on width of the main lobe of w to the power j omega. A secondary effect of windowing is that the ripples from the side lobes of w to the power j omega produces approximation errors for all omega. So based on the above discussion, the desirable characteristics can be listed as follows. So this I have already discussed. The Fourier transform of the window function should have a small width of main lobe containing as much of the total energy as possible. The Fourier transform of the window function should have side lobes that decrease in energy rapidly as omega tends to pi. Okay. So this is the we have discussed about the window function. Okay. So so now if we will see, this is basically the main lobe, this is the main lobe. So how this main lobe represents in the filter? So when you will design an FIR filter, then correspondingly the you can say the width of main lobe will corresponds to the transition bandwidth, means main lobe width will be equal to transition bandwidth, and here you can see this transition bandwidth is dependent upon the window function you are using. Okay, so main low width will be equal to transition bandwidth. Okay, so if the main low width will be more, then transition bandwidth will be more, and if transition bandwidth will be more, then what happened, then switching will be slower. So how can we control this main low width? Main low width can be controlled using the filter order. So if we will increase the filter order, if we are, let us suppose n is the order of the filter, and if we are increasing the filter order n, then transition bandwidth will become less. Okay, so this is basically the compromise that we have to make here. Okay, now we will come through the window functions. We will see different types of window functions. Like first function is you can say this is the rectangular window function, this is the rectangular window function. So here we have seen two types of expression. One expression is this for window function, another one is this. So for each and every window function, we can write window functions in two ways. First way is to write the window function in non-causal form, but it is mandatory that when you are taking non-causal window function, then it should be symmetric, means symmetricity about the origin must be there, otherwise it would be causal. So if you will see the symmetric window function, then you can see n lying between minus n minus 1 by 2 to n minus 1 by 2 will be equal to 1 and 0 elsewhere. And in case of causal window function, this value will become 1 between the interval 0 to n minus 1. Okay, so this is the first version. So you can say, for let us suppose you are taking a window function of length 5, rectangular window function of length 5. So how you will draw this window function of length 5 in symmetric case? You will see the value will become from minus 5 minus 1 by 2 to 2, yani minus 2 to n is lying between minus 2 to 2. So if you will draw this window function, you are simply this is the center of symmetricity. So this is the value corresponding to minus 2, minus 1, 0, 1, 2, and each and every value will become 1 in magnitude. Okay, and similarly if we will see the causal window, then in the case of causal window, what happened? This we are providing the amount of delay that will be equal to n minus 1 by 2 is 2. So what will be there? Then this window function will start from here, 0, 1, 2, 3, 4. Okay, so this is the first window function. But when we will use this type of window function, we have already seen when we will use this type of window function, then the truncation of infinite duration impulse response will become abrupt, not gradual. So what happened? When this will become abrupt, then we will have undesirable oscillations in the pass band and stop band. So what we have to do basically, now we have to change the shape. If you will see the envelope, what is the envelope in this case? This is the envelope, or this is the envelope. So your envelope is of window function. You can see here the slope is infinite. Okay, and we are trying to obtain, we are trying to truncate this infinite duration impulse response using a window function which is having infinite slope here, which cannot be possible with finite number of terms in the window function. Okay, so this is not possible. So that's why we are getting undesirable oscillation. The solution is we can change some other window function where the truncation is not abrupt one, but it is actually the gradual one. So another type of window function is modified rectangular window function. In modified rectangular window function, we have done some change in the rectangular window function. What we did basically, here we can see that first and last samples all are 1, but what we can do, if we will make first and last sample value as 1 by 2 rather than 1, so you are having this type of response again for n equals to 5. Okay, so this value will become 1 by 2, this value will become 1 by 2, 1, 1, 1. Now if you will draw the envelope here, your envelope will be like this. So you can say here there is infinite slope, but here there is not infinite slope. So you can say you have resolved the issue up to some extent in case of modified rectangular window function by putting first and last sample value as 1 by 2. Okay, so slightly modification will be there. So the results, if you will see the oscillations in pass band and stop band, that are, you can say, resolve up to some extent, not not very much, but up to some extent we are able to reduce the oscillations in the passband and stopband. Then comes to another window functions like Henning window function. So Henning window function is explained here. So this is for causal one and this is for symmetric one. Okay. So in causal causal window function, we can see the expression is 0.5 minus 0.5 cos 2 pi n upon m minus 1, and here 0.5 plus 0.5 cos 2 pi n upon m minus 1. Okay, only sign will be changed. So if we will see, if we will take Henning window function causal and we are taking capital M equals to 5, capital N or capital M, you can take anything. So now if you want to calculate the coefficient like W hen 0, so according to this expression, when you will put n equals to 0 here, this is cos 0 and it will 1. So this value is 1. And also if you will calculate W hen last value, let's say 5. So you are varying the coefficient from 0 to m minus 1, which means last value is 4. So if you will put value 4, so this will become 0.5 minus 0.5 cos 2 pi into n value will be 4, and here again 4. So cos 2 pi is 1, again it will become 0. So you can see in Henning window function, the first and last coefficient value of window function will become 0. Okay, so effectively you can say only m minus 2 terms will be in window function. Okay, will be in window function. And if you will see, we will calculate the value and draw the envelope. So we are having envelope of somewhat this type. This is for Henning window function. Okay. Similarly, for symmetric or non-causal case, we are having expression like this. Another modification is Hamming window function. In Hamming window function, Hamming done some changes here, which was in Henning window. Here the coefficient values are changed. Here the values, rather than 0.5 we are taking 0.54, and rather than 0.5 we are taking 0.46. Otherwise the expression is same in both the cases, like first one is causal one and second one is the symmetric one. Okay. Now if you will see the first and last hem, let's say again case we are taking m equals to 5. So this value will become 0.08, and also W hem at m minus 1, that will become 4. This value will become 0.08. So your envelope will be slightly changed. How slightly changed? It will be somewhat, this value is not 0, first and last value is not 0, but it is somewhat like this. Okay. So these are the functions defined by these are the window functions defined by the scientists, various scientists, like Hamming has given this, Henning has given this. Okay. So now when we are using this type of window function, then we will see that the results are somewhat improved. Result in terms of what? Result in terms of, you can say, side lobes, lesser number of side lobes. One important thing is that there are two types of lobe, major lobe and side lobes. So major lobe width is proportional to transition bandwidth. Okay. So major lobe width can be reduced or increased by controlling the value of order m. By increasing filter order m, we can reduce the transition bandwidth or major lobe width, but there is no control over the side lobe width. Okay. So there is no control over the side lobe width, but the side lobes are basically the functions of window shape. What type of window shape you are taking, based on which truncation will be. If you are taking the window function shape like that, the truncation will be more and more gradual. If the truncation will be more and more gradual, then lesser number of side lobes will be obtained or less spectral leakage will be there. But as soon as you will make your window function more gradual, then what happened? You are having a larger transition bandwidth. Okay. So this is basically, you have to do a compromise that which window function you will taking, and you will design a FIR filter at which window function, and for that window function what optimum filter order you should have to choose. Okay. Then next one is Blackman window function. So Blackman has added some extra cosine term. So it was seen by the Blackman that after adding a extra cosine term in the window function, number of side lobes can be reduced significantly. Okay. So what basically Blackman did, it will add this term, Blackman added this term and also modified these coefficient values defined by the Hamming and Henning previously. Okay. So these are the expression for, you can say, causal Blackman window, and this is for symmetric Blackman window. So if you will see the Blackman window function, again it is a raised cosine type of pulse like this. Okay. So you can say Hamming and Blackman. If you will see, then you will find that there is a smaller difference between all these three. Okay. So if you will see the Blackman window function, the width of the main lobe is approximately 12 pi by m and the peak of the first slice lobe is minus 58 dB. Okay. Then last one is the Bartlett or triangular window function. We can call it Bartlett based on the name of the scientist, and triangular is the shape of the window function. So it was seen that if we will take the window function envelope like this, okay, then the response will be, then you can say the truncation will be more gradual. Truncation will be more and more gradual. So when we are using this type of window function, then because this response, it is the truncation will be gradual, so less number of side lobes again in the pass band and stop band. Okay. So here we can see for non-causal or symmetric one, the formula is 1 minus 2 mod n upon n minus 1, where small n is varying between n minus 1 by 2 minus n minus 1 by 2 to n minus 1 by 2, and here it will become 1 minus 2 mod n minus 1 by 2 upon n minus 1. Okay. Here we will see the main lobe width is now 8 pi by n or twice that of the rectangle window. Now we will see a comparison of different window functions. So here it is the important one. We are taking 5 window function: rectangular, Bartlett, Henning, Hamming and Blackman, and we will see the transition bandwidth for rectangular, it is the lowest one, then for 8 pi by m for Bartlett, Henning and Hamming, and 12 pi by m for Blackman. Means the transition bandwidth is more in case of Blackman as compared to for similar filter order. Okay, so this is basically disadvantage, but we will see at the expense of larger transition bandwidth, we are also reducing the number of side lobes. So here you can see the attenuation is more in case of this. So minus 21 is less than minus 25, minus 44 and minus 53. So it means Hamming will give the better result as compared to this with the same transition bandwidth, and here we will see minus 53. It means the attenuation is higher here. Okay, so Hamming you can say use, and if you will use Blackman, then you will get more lesser number of side lobes as compared to Hamming, but the expense of higher transition bandwidth. Okay, so if you will compare this, you can see these are the various envelopes of window functions. Like first one is the rectangular one, so this is the rectangular one. Okay, second one is the Henning one. So Henning is this, you can say first and last value is 0. So this one is of, this one is basically of Henning. And what about Hamming? This one is Hamming, you can see 0.08 and 0.08 value will be there. And this is the Blackman. You can see in Blackman again first and last value is 0, and but you are having this type of response. One more, if you will draw the triangular window function, it is somewhat like this. Okay, so this is, you can say, triangle or Bartlett window function. So this is the comparison among the window functions. Now we will see how we will design FIR filter using windows. So the procedure for designing FIR filter using windows is: choose the desired frequency response of the filter, take inverse Fourier transform to obtain the desired impulse response SDN, choose a window sequence Wn and multiply SDN by Wn to convert the infinite duration impulse response to a finite duration impulse response. Then transfer function Hz of the filter is obtained by taking jet transform of Hn. You can also obtain He to the power j omega. How? He to the power j omega, or frequency response we want to obtain, simply put Z equals to e to the power j omega in the expression. You will get the frequency response also. So this is one of the numerical that I have taken. So a low pass filter is to be designed with the following desired frequency response. So this is the desired frequency response. So you can see this is the specification for pass band, and the pass band is from minus pi by 4 to pi by 4. It means this is a low pass filter. Okay, Determine the filter coefficient HDN if the window function is defined as omega n equals to 1 for 0, n is between 0 to 4 and 0 otherwise. Because n value is given from 0 to 4, it means we are talking about causal rectangular window function. And also determine the frequency response of the design filter. Okay, so it is given to us. So first of all, we will calculate the value of HDN. Okay, so HDN is calculated using this expression 1 upon 2 pi minus pi to pi HD to the power j omega into e to the power j omega n d omega. Now, it is from minus pi to pi, but our passband is limited to minus pi by 4 to pi by 4. So this limit will be minus pi by 2, pi by 4 to pi by 4. And HD to the power j omega is e to the power minus j2 omega into e to the power j omega and d omega. Okay, then we can solve it, e to the power j omega and minus 2 d omega. Now, if you will integrate it, so simply you are getting e to the power j omega n minus 2 upon j times n minus 2, and the limit is from minus pi by 4 to pi by 4. Okay, so you can solve it. So after solving, HDN will become 1 upon pi minus pi times n minus 2 sin pi by 4 n minus 2, because when you will put the limit, you are getting the term e to the power j n minus 2 pi by 4 minus e to the power minus j n minus 2 pi by 4. So e to the power j theta means cos theta plus j sin theta minus cos theta minus j sin theta. So what happened? Terms of cos will be cancelled, and here you will get the term of sin. Okay, so sin term will be there, 2j sin n minus 2 pi by 4 upon 2j will be cancelled. So you are getting this term. Okay, so now we are having HDN. HDN is our desired impulse response. HDN is our desired impulse response. But you need the coefficient values, like here n equals to 5. Okay, here n equals to, here length of the window function is given as 0 to 4. It means m equals to 5 is given to you. Okay, so you will calculate the coefficient values. For n equals to 0, you will calculate. For 1, you will calculate using this expression, but when you will calculate for n equals to 2, you are having 0 by 0 form, so you cannot directly calculate it. You have to use L'Hopital rule for calculating it. Again, because we are dealing with FIR filters, so in case of FIR filter, there will be a property of linear phase. So this property says that H0 will be equal to H4, H1 equals to H3, and H2 will be there. So you have to calculate only these three coefficient values. Okay, other coefficient values will be accordingly. Okay, so if you will solve this using L'Hopital rule for n equals to 2, HD2 equals to 1 by 4. Similarly, when you will put n equals to 0 in it or n equals to 4 in it, you will get HD0 equals to HD4 equals to 1 upon 2 pi, and HD1 equals to HD3 equals to 1 upon under root 2 pi. You will simply put n equals to 0 here, n equals to 1 here, and n equals to 2 here. For n equals to 3 and n equals to 4, the value will be equal to correspondingly value of 0 and 1. Then, so these are the coefficient for desired filter. Now for designed filter, coefficient will be obtained like Hn equals to Hdn into Wn. Okay. So here, because our window function is rectangular one, so whatever the value of Hn is there, you are having the value of Hdn. Okay. So Hdn and Hn coefficient will be same in case of rectangular window function. So similar are the coefficient values of Hn. Now you have to calculate the frequency response of the designed filter. So you will simply write h e to the power j omega summation n equals to 0 to 4 hn e to the power minus j omega n. Then you will solve it, h0 plus h1 e to the power minus j omega, like this. You are getting this expression. Now important thing is that when you are making a filter, this filter need to be realizable and causal also. So we have to take a term e to the power minus j omega alpha, where alpha equals to m minus 1 by 2. Here m is 5, so this will become 2. So you have to e to the power minus j omega 2 term should be there, which is used for making this function as frequency response as causal. So what we will do, we will take e to the power minus j2 omega term outside, then h0 e to the power j omega. Accordingly we have changed this. Okay, now you know h0 will be equal to h3, h0 will be equal to h4, and h1 equals to h3. So you can take h0 common as, so e to the power j2 omega and e to the power minus j2 omega term will be there, and h1 and along with h1, h3 term will be combined. So e to the power j omega plus e to the power minus j omega. Then you will write the, then you will put the coefficient values 1 by 4 plus 1 upon 2 pi plus 1 upon under root 2 pi like this. Now what is the value of e power j2 omega plus e power minus j2 omega? Cos 2 omega plus j sin 2 omega plus cos 2 omega minus j sin 2 omega. So this value will become 2 cos 2 omega. Similarly here, this value will become 2 cos omega. So when you will put, you are getting this frequency response of the design filter. So if you will see, if you will take the mod of it, then this e to power minus j2 omega mod will become 1. Okay, so this is the basically the magnitude, you can say. Okay, so this is how we will design a FIR filter using window techniques. Here I have used the rectangular window technique in this particular question. If some another window function will be there, then you can solve it accordingly. In that case, what happened? This W will be changed, and accordingly we will multiply this HDN corresponding window function values. Then we are having HN values different from HDN, and accordingly the response. Okay, so the reference is Digital Signal Processing by S. Sullivan, 3rd edition. Thank you so much.